This Zoom session is being brought to you by the fractal octaves. It's one of my favorites. Octaves S in the, oh, wait, yes. Octaves S in this case. Next time will be octave Z. All right, for today, we'll be graphing the secant, cosecant, tangent, and cotangent functions. All right, the secant is the reciprocal of the cosine. So whenever cosine is 0, secant is infinity. That happens for x equal n½ pi for integer values of n. Excuse me, that should be an n, not an x. I'll have to change that. Just a moment. Okay. And secant of n times pi n times pi is -1 to the nth power. And we can see that happening here. Here it is at 1, -1, 1, -1, 1, and so on. And halfway between it goes to infinity. The cosine is going to up, then down, then up, then down. Excuse me, Nielsen. The secant goes up, then down, then up, then down, then up, then down. And the reciprocal goes from infinity to 1 to infinity, minus infinity to -1 to minus infinity, positive infinity to 1 to positive infinity, and so on, oscillating like this. I like to think of this as somehow, when cosine oscillates through 0, secant oscillates through infinity. Cosecant is reciprocal of sine, and so it equals infinity at integer values of n times pi for integer values of n, and it's plus or -1 for integer and a half multiples of pi. So cosecant n pi is infinity, cosecant of n½ times pi is -1 to the n. 1, -1, 1, -1, and so on. This too oscillates through infinity. And it does so with a quarter cycle phase difference, just like cosine is and sine are a quarter cycle phase different. Tangent is secant over cosine. So it equals 0 when sine is 0, sine over cosine, excuse me. And so tangent of n times pi is 0, because sine is 0 at those points. It equals infinity at n½ times pi, because cosine is 0 at those points, and it's division by 0. So now, so we have an infinity, a 0, and infinity, a 0, and infinity, a 0, infinity, 0, infinity, and 0. Okay, what's not so obvious is that it's going kind of constantly rising like this, making what I call an n-shaped graph. Whereas cotangent, it's always rising, and has period pi. Cotangent, cosine over sine, it's 0 when cosine is 0 at n½ times pi, and it's infinity when sine is 0 at n pi. So here it goes infinity, 0, infinity, 0, infinity, 0, infinity, 0, infinity. And what's not so obvious is that it's always falling, making these S-shaped curves with, again, period pi. Now, if you have an omega x, secant omega x and cosecant omega x, you have to reduce the period by a factor of omega. So these have period 2 pi over omega. Tangent and cotangent have period pi, so tan omega x and cotangent omega x have period pi divided by omega. All right, graph y equals tangent of pi halves. All right, the period is pi divided by pi halves is 2. So, and plugging in 0 in for x, you get a 0 when x is 0. Therefore, 0 at 2, at 4, and infinities at 1 and 3. And because this is a tangent, it's constantly rising. So at 1, it's infinity, -1, it's infinity, to 0 to infinity, infinity to 0 to infinity, and so on like this. Here's cotangent of a quarter x. Period is pi over a quarter, which is 4 pi. So putting in 0 for x, you get cotangent of 0, which is infinity. So it's infinity at 0, at 4 pi, at 8 pi, and so on. And halfway between it's 0 at 2 pi and 6 pi, and so on. So infinity, 0, infinity, infinity, 0, infinity, and so on. And because it's a cotangent, it's constantly falling. Here we have y equals 2 secant x. Period is 2 pi over 1, because this is 1x, so that's 2 pi. And, okay, let's plug in 0 in for secant. You get twice secant 0, which is 2. So it's 2 at 0, at 2. At 0, it's 2. It's minus 2 at pi. It's 2 at 2 pi. It's minus 2 at 3 pi. It's 2 at 4 pi, and so on. And infinity at the halfway marks. Pi halves, 3 pi halves, 5 pi halves, 7 pi halves, and so on. So at 0, it's 2. At pi, it's minus 2. At 2 pi, it's 2. Negative 2 at 3 pi, up, down, and infinities in between. Here we have secant of 2 pi over x plus 2. This plus 2 means we lift it 2 units. So we have to do a little bit of a lifting. So it's centered around 2 like this. Period is 2 pi divided by 2 pi over 3 makes 3. Plugging in 0 in for x, you could secant 0 plus 2 makes 3. And so it's 3 at here, at 0, at 3, at 6, and so on. Halfway between these 3's, it's negative 2 plus negative 1 plus 2 is a 1. So it's 3, 1, 3, 1, and so on. And halfway between the 3's and the 1's are the infinities. So therefore at 3/4, at 9/4, at 15/4, at 21/4, and so on. So at 0, it's 3. At 3 halves, it's 1. At 3, it's 3, 1, 3, 1, etc. And halfway between, we have these infinities. Frankly, I think it makes more, yes, you can know how to do this sort of out of your head and so on, but I think it's entirely valid for you to use a hand calculator or some kind of graphing capability to do this, because that's sort of what it's for. And it's just, and also, let's face it, secant, cosecant, tangent, and cotangent are messy with all those infinities. And so it's, mathematicians try to avoid having to graph those things. For that reason, most of the problems here we'll see involve sines and cosines. Well, okay, that's this for this. Next time, I'll use octaves Z instead of octaves S. We'll talk about shifting phases on sines and cosines. So we have, instead of a sine omega x, but a sine omega x plus phi, or a cosine omega x plus phi. What this phi does is that it shifts the phase of it, moves the graph left or right by a little bit. And so you would have this, or this, or this, or this. We'll see more about that later. Okay, I think that'll do for now.